102. Uh, Thank you for joining us again. This is the second session, and this session will be focused mainly on the programming aspect of neurul. Okay, so where's the cheat sheet? All right. So again, just like the previous sessions, please mute your microphone when listening, and unmute the microphone when you want to ask questions or during discussions. Use your webcam so we know if we are getting you excited or sleepy. So we really appreciate it if you can just show yourself, so we know that we're actually talking to people, not bots. And leave comments and suggestions in the neurul channel of Fibonacc after the session. Right? So just a quick recap of our previous session, neurul 101. So in the last session, we recognized the problems common to all internet users today. And we understood the proposed solutions to these problems. The two solutions were to have a universal language that we can use to compose an organ or a brain for additional brains for our users. Then we saw how the neural-powered future looks like. We went through some samples of how neural can improve our lives and what solutions it may bring us. Then we went through some basic theories and hypotheses in neuroscience. And we then looked at neuroscientific concepts and how we could use them to code in neurul. All right. Now the objectives for today's session are the following. Oh, by the way, this session is really a review. So feel free anytime to butt in. If you have any suggestions or comments, questions, feel free to interrupt me at any time. This is a review session, and we're still trying to make sure that it's easily understood. And if it gradually or effectively grows on the ideas which were discussed in the previous sessions. Right. So the objectives for today's session would be to discuss MIT 6.001 Lecture 1A, which is the YouTube video that we sent earlier. This is the recommended resource. Then we wanted to look at additional topics in neuroscience. And so we could understand more the concepts that are needed for us to be able to work effectively with neurul. Then we would like to compare neurul and Lisp mechanisms. So as you may have seen, the Lisp language or programming language is the language which is used in the MIT lecture. Then the next is we're going to play a mystery game. So it's a very small game that we're going to do, actually, but not in this session, but maybe in the following sessions. Because I think it's best if we do it at the actual recording that we're going to make for this session. Then finally, we're going to neuralize or convert the samples in lecture 1A into neurul. So we'll show and demonstrate that neurul is actually able to perform programming functions that modern day programming languages perform as well. All right. So we will start with a quote from John Locke. So he's an English philosopher and physician. He is known to be the father of liberalism. And in 1689, he had an essay, and it was a landmark essay. And I think the title is The Essence of Human Understanding. And he basically outlined three concepts or three things that our mind does, right? So basically it's combining, linking, and abstracting, right? And it's very easy to Google search this essay, and it's a very good one. I haven't been able to read the whole essay, but this was mentioned in the later lesson. I think if not in this lesson, in the subsequent lesson of the MIT 6001, and I think in the book as well, because this forms the basis of structure and interpretation of computer programs. Right. So let's discuss MIT 6001. What were the points that were mentioned there? So first, the professor said that computer science is not really about computers. Much like quantum physics is not about particle accelerators. It's not about the instruments that you use for your discipline. And he's also saying that it's not really a science. It's more like magic, because what you're doing is you're creating stuff out of nothing and making them do things for you. So that's basically his explanation why he likens it more to magic than science. Then he also discussed knowledge and the two types of knowledge that we are dealing with. So declarative knowledge is like geometry, when you're establishing relationships between known truths. And so that's called declarative knowledge. The other type of knowledge, which is what we're dealing with in computer science, is called imperative knowledge, which is basically the how-to knowledge, or knowledge of processes, procedures, and code or languages, and how to use those things to make changes in your systems. So computer science, to sum it up, basically he said that is a business of formalizing how-to imperative knowledge. Okay, so he also went through some terms, the first of which is the process. What is a process? So if we're going to continue the analogy of computer science as a form of magic, or as a type of magic, then we can say that process is like a magical spirit, that lives inside a computer and does something. Now, procedure is like a pattern of rules that direct a process. So it's like your magical spell. So I don't know if you've seen Harry Potter. I haven't really watched the whole series of those movies, but it's like what the procedure is, the call that you make. It's like the call that you make to cast a spell, or to cast something or a change to occur. Then finally, language, or programming language, is the actual language for casting a spell. So I think in Harry Potter it's Latin. I can't remember the exact language that he was using, but it was a strange language that he would use to invoke the beings and the changes that he wanted to happen in the movie. And then he said in the lecture that unlike other kinds of engineering, computer science is not constrained by physical systems, right? And unlike construction, civil works, so on, electrical engineering, most of it is constrained by limitations of your physical devices, or of your physical resources. Computer science is different because you're not limited by space and time. You're able to replicate your objects in your system as many times as you want. So that's why we're able to scale and grow our systems indefinitely. But of course, it's limited by physical resources of the machines. But the point is that it's much more flexible and it's much more portable, because these are all abstract concepts that we're dealing with. And it's basically as unlimited as the minds of the developers. So you can really imagine anything, and you can do anything and create anything in cyberspace, if you will. All right, so what were the big topics mentioned in the lecture that we're going to use to control complexity? So the first topic is called black box abstraction, or otherwise known as the programming language mechanisms. So these are the things that we use to create code, or to manage the objects in the system, or to work with the system. So the first one is the primitive objects. So these are in Lisp. In the Lisp programming language, these are simple data such as 1 plus A, B, or the word Steve. So these are what we work with. These are the primary elements that we work with. Then in Lisp, there's a means of combination, which was shown, which is, for example, addition. And this, I'm just going to share my pointer. And this line here is a combination of an operand and then the primitive objects. And it's basically telling the Lisp program to add these numbers. So that's how it uses combination to process addition. Then next is the means of abstraction, which is basically the way of defining a function or a new object so that can be used by other objects without knowing the internal details of that object. So those are the three main mechanisms for programming languages in Lisp, right? Then he also mentioned that he will be discussing conventional interfaces, and these are very well-known constructs in engineering. So I'm sure you're familiar with a USB cable, right? So if I just get a USB cable here, with using the idea of conventional interfaces, developers are able to create multitudes of devices that they can use to integrate systems. And by just defining a conventional interface like this USB cable, then regardless of the devices that will be using or will be interacting with our system, we know that it will work, and it will easily work because this conventional interface is being followed and agreed upon by different entities who are participating in the same ecosystem. So let's say Sony can create a device which uses USB, and Apple can use a device which uses USB. Then the systems which will be using USB will be able to use those two devices without being concerned about the internal implementations of those devices. So that it makes it very simple. And the next topic is metalinguistic abstraction, which is about using a language or creating a language to simplify abstractions and simplify concepts, which is actually what we're doing in neurUL. Basically, we're creating a language which is based on the biological neural network to contain this abstraction that we're working with. Right. So, by the way, before we go into the neuroscience section, are there any questions regarding the lecture? Were there some points there that you think needed points of clarification? That's fine. Okay. All right. Okay. All right. So let's just go through the neuroscience topics, the additional topics that we need to familiarize ourselves with. So I think there are a couple of topics from the previous session that I'll be transferring to this session. But for now, since we've been through, and I'm sure you've watched the previous videos as well, in this session, we'll just be going through a couple of slides for the additional concepts. So the first one is the action potential. So in the previous video, we went through it very quickly. So there was just one video in that video which showed how an action potential propagated from a dendrite to the soma of a neuron and then to the terminals of the neuron, right? But here we're going to go into detail of what happens in an action potential, right? So each neuron in our nervous system has a resting potential, which is negative 70 millivolts. So when nothing is happening, when there's no electrical signal going through a neuron, it is resting at negative 70. Now, when there's a stimulus wherein, let's say it receives a neurotransmitter, which excites it and depolarizes it, meaning increases the voltage, then, so when there's a depolarization going on, then the charge will go up, right? So it will go up, But if nothing happens, it will go down again, right? So it always tries to rest and maintain this resting potential. If it receives a charge, it will go up, it will depolarize. If it depolarizes enough to the point that it reaches 55, then it will fire what's called the action potential. If it doesn't reach negative 55, it will go to a state called failed initiation. So it will only go up here and then go back again to the resting potential. But if it reaches negative 55, it will fire. So it will be flooded by positive ions, and then it will shoot up and fire. So you can imagine that each neuron is actually like a machine. So it's just waiting for input. And if you trigger it enough, it will fire forward into other neurons. Now, it's not mentioned here, but there is a time. There's a time difference between between the time when it can receive spikes and the time that it cannot receive spikes. So I just forgot the name. Maybe I'll put that in the next session. But if it is performing a spike like this, then regardless of how many times you spike it, or let's say it's hyperpolarized, because what happens is once it depolarizes here, it will try to suck in, flush out positive ions, and then it will try to go negative further. So this will reach up to maybe negative 100 millivolts. And during this time, regardless of how many times you spike it, it will not process that stimulus because it's way negative. So there's an amount of time between when it can receive a spike, which is from here to here, and when it cannot receive a spike or process a spike. So if it's around this time that it receives a spike, it won't do anything. It won't process that voltage, and it will just stay below 70, right? So that's basically it. That's how the action potential works. Okay, so that's the details of how it happens, and this information is very important because this controls how you may require multiple neurons to fire in order for another neuron to fire. So you may remember this in the previous session on interneuron. So we were saying that react when Jennifer is seen, or a funny actor is seen, only when react when actor, funny, and then are seen, right? So only when those 3 or 4 neurons are fired will the interneuron fire and forward that to another neuron. So let me just show you, just maybe to jog your memory. And I think it will be good to show this slide then in this current slide, so you may see. So neurul 101. Right. Right, so for example, here, react when sexy actor seen. So this will only spike if all 4 of these fire into it. Because let's say the synaptic strength, which we'll discuss in the next slide, the synaptic strength is 0.25, then each of these will only contribute to a quarter of the required charge, which will spike, which will cause this neuron to fire forward to call a friend. Okay, does that somehow make sense? Is that right? Yep. Okay. So let's now go to the next slide, which is, synapse. So remember, the parts of the neuron are the dendrites, the soma, which is the middle, and at the ends of the axon is the axon terminal. So these are the connections between a presynaptic neuron and a postsynaptic neuron, right? And each of the terminals actually contain a synapse, or is represented by a synapse, right? So the synapse is the space in between the neuron, or the actual combination of the terminal, the space, and the surface of the postsynaptic neuron. So a synapse has two parameters that we are concerned with in terms of neural. So the first is the strength. So the strength is basically the amount of charge that carries over or reaches the postsynaptic neuron coming from the presynaptic neuron. So if it's 1, if the value is 1, so it's basically a float, or just a value from 0 to 1. So if it's 1, then a charge will be converted fully or forwarded fully to the postsynaptic neuron. If it's 0.5, then it's just half. So it will require 2.5 action potentials for the next neuron to fire. So it's just a ratio, So it can be 0.33. So that will require 3 neurons, or presynaptic neurons, to fire the postsynaptic neuron. So that's the strength. Okay. Now, the other neuroscientific concept is neurotransmitters, and neurotransmitters can either be excitatory or inhibitory. There are only 2 types of neurotransmitters. Different neurotransmitter compounds may exist, but essentially these neurotransmitters only do 2 things. Either they excite or depolarize the neuron, or the postsynaptic neuron, or they hyperpolarize or make the charge further negative. So those are the only 2 things that it does. Okay. Now, these are details that we don't need to be familiar with, but okay. But if it's excitatory, it uses the glutamate neurotransmitter, or if it's inhibitory, it's the GABA, or the gamma aminobutyric acid neurotransmitter. So only those 2 are used. So inside the cell, again, just to recap, inside the cell, it's electrical. And then when it reaches the terminal, it converts into a chemical reaction, which is the release of neurotransmitters. And when it reaches the postsynaptic neuron, it converts into electrical again. All right, so that's the flow of the neurotransmitters. All right, so are there any questions before we proceed further? Is that clear? Okay, cool. Right, so now let's compare the mechanisms between neurul and Lisp, right? So in Lisp, as we said earlier, the primitive types are, for example, 1, plus, A, B, and Steve. So as you can see, it uses actual data objects to refer to primitive data, right? So these are when you code, this is what you use. So you have 1, 5, 6, you have close parenthesis, open parenthesis, and then operand plus, and so on. So these are Lisp. In neurul, however, it's different in that there's no such thing as data. The actual primitive data in neurul are the structures that support the data, or the perceptions and the actions. So these are the neuron. You have an ID for the neuron to be able to identify a neuron, and then a tag, which is just the name of the neuron, right? So it is part of the means of abstraction that we'll discuss shortly. So we are tagging neurons to be able to abstract details further. So we may, for example, in this case, we may say that a robot poodle is a robot and a poodle at the same time. So that's our means of combination via linking. We can provide as much detail as we want via linking, or we may not do that and just stick with the fact that this is a neuron and we don't care about the further details as a method of abstraction. Just so if I can cover this section here, this is just a robot poodle neuron, and that's it. Right, so then there's a means of combination. In Lisp, since the user interface is two-dimensional, you have like a text-based programming language. It's just open parenthesis plus 156. So you have row and column of text. However, in neurUL, it's multidimensional. You're not limited by two-dimensional text editor. You are basically linking a network of neurons with one another to create code and to create imperative knowledge, as you can see here. So just to give a bit of explanation, okay, we'll do that after we explain the means of abstraction. So in Lisp, you use define to define your objects and to define your functions. However, in neurUL, you're able to create abstraction just by just adding a name to your neuron. So you can create a neuron, let's say animal, and just add a name to it. Now, you may add relationships later on, but it's up to you. And you can do it as necessary, and as you want to code it. So as you can see here, just to explain what this means. So let's say neurUL is a language that we would use to understand this. Basically what it's saying is a dog is a type of an animal. A poodle is a dog. A poodle may be a cat. We're not sure yet. That's why it's 0.5, because it's cute or whatever. But the main point in neurUL is that you are free to define your concepts as you want. There's no limitation. So this is part of what John Locke was saying in his essay, that children are born without innate ideas. And that's why we gradually grow those ideas through time as we go along. And that's why when you have your own neural brain, you're then free to define your concepts as you want. Okay? And then a poodle, a robot poodle, is basically a combination of a robot, so which is the means of combination, and the concept of the poodle. But of course, since robot poodle is not an animal, we create an inhibitory terminal. So that's why it's red. And we will show that in the next session, wherein we'll have a hands-on exercise of neurUL. So we'll download and then run neurUL on our own machines. Okay. So those are the differences between neurUL and Lisp that we have seen so far based on the resources we've been through. Okay. Are there any questions wanted to clarify? Okay, that's all right. Right. So the mystery game. The prize is a very simple prize, but it's a nice one, and I hope you'd be excited about it. It's a Google Cap. It's a Google Cap. It's much like this one, but this is better because this is colored, letters for Google. Hopefully someday we'll have a neurUL cap or a dash cap, but that's for later. For now, the prize is a Google Cap. And unfortunately, we won't be playing this game today, but in a subsequent session, so I'll keep you posted. And the game is about a very special moment in the video, in the neurUL 6 and in the MIT 6.001 video. So it's about 10 seconds, 20 seconds segment. And so it's like a finders keepers game. You just need to tell me the time, and I'll give the question once we play the game. So you just need to tell me the time point in that video which we're looking for, okay? So it's very important, and it's very much connected to what we're doing, okay? Right, so the following part of this session is just to convert the samples that the professor showed in the lecture. So we're going to convert them into neurUL and translate them into neurUL. And we're not going to use the Dash Neural Studio yet to develop the samples. That will be in the next session. But we're just going to use graphic images like this one to show how it's being done. Okay. Right, so to summarize the session, we will go through, we would have discussed the details of the MIT 6.001 lecture. Then we would have understood the additional topics in neuroscience. So as I said, we'll be transferring some of the topics which I think are not really important in neurUL 101, and we may transfer it here. So, you know, participants will not get too overwhelmed with the first session. Then, and of course, let me know if you think what we've discussed so far in this session is complicated, or you know, if you think it's too much, or if you think you want more details, just feel free to let me know at comments in our channel. Then we have compared neurUL and NISP mechanisms. So we can see that neurUL actually represents programming languages. And soon we may be able to replicate human languages as well. And we're hoping to show that in the subsequent sessions. Then we played the mystery game, and we basically pointed out a very important part of that video, which is related to neurUL. And then we have neuralized the samples in lecture 1A. So what's next? In neurUL 103, we look at the architecture of neurUL, how it's been implemented as a software application. We'll then go through how we download, set up, and run the neurUL Studio in a Windows machine. Unfortunately, we're not able to support Apple at the moment, but it's in Windows. And you may need to have a Windows machine to be able to run it as well. Then we'll look at the Dash user interface. So how do we use and understand the interface so we can create our own neural network? And we will then use the Dash application to actually neuralize and test the samples in sessions 101 and 102. Then the following are just a list of topics that we may go through for the last, not really the last, the next session, which is 104. But it's like, I think it's a graduation session, I'm hoping, because it will then show participants what they should be able to do with neurUL, you know, once it's fully implemented. And actually, even now, we can start working on some of this stuff. That's where we need the help of contributors to work with this. So the first one is the metalinguistic abstraction. So this was mentioned in 6001, basically the creation of a language using neural concepts. And this is quite an effort because, yeah, I think we're the only ones doing this at the moment, which is converting or creating a language based completely on programming languages and supported by technology to do that. Next one is to create a section in neurul.net. So we have control of the website neurul.net, so that URL. And our hope is to create a brain which documents and which will serve as the dictionary for the English language. So it's like a Wikipedia of English words and English language structures and so on. And so this is just a start. Hopefully soon we'll explore other languages like, for example, Japanese, Chinese, Filipino, you know, and German, whatever we think will be necessary to hopefully enable anyone, any human who wants to code, you know, not like right now. To be able to learn a programming language, you need to learn English, etc. So after that, we'll look at the heart rate monitor, which is the prototype app that we have. Then, which uses neurUL, and then we'll show you how you can create your own app, how easy it is, and yeah, as the subsequent sessions will be on, setting up your own server, creating your own brain at home, and then connecting them as you want. All right. So yes, that's it. That's neurUL 102. Please, let me know if there are any questions, clarifications, any comments regarding this session. Further details needed, or if you think it's too much.
It's fine.
Yep. Mm-hmm.
I think it's fine. It's shorter than than 101. Like, I think 101 went for an hour and a bit rate, so maybe you just want to spread the two. I don't know. No, it's fine though. I think the only thing I think is maybe how, like, the explanation, if you go back to the slide that you use that actually has the pictures of the neurons and how they work. I get what you were trying to say, because you were talking about refractory periods and stuff like that, so they can't be triggered, which is basically that one. So that is a refractory period.
That was the word I was looking for, actually, Michael. Thank you for that.
I didn't want to interrupt you though. But so obviously in the refractory period, it can't be repolarized, because even if it was, it wouldn't. Basically, the hyperpolarization would
to tell you
depolarization. But what I'm saying is that might be too much of an explanation.
Okay.
Like, I think don't necessarily get into this, how neurons are triggered too much. Because from what I'm gathering, based on this and then the next slide, so if you go to the next one, right, where you're explaining this, I almost think that you don't need this slide. Well, you only need this slide, but maybe a better picture, because what I think a lot of people won't understand is that neurons look like, a lot of diagrams will just have a single neuron which goes to the surface of the follow-on neuron, so it passes on the message. But what you're talking about with strengths, which is why I think a different picture would be better rather than excitatory and inhibitory, is that a single neuron might need the impulses from 2 or 3 neurons that are connected to it for it to actually trigger that follow-on neuron, which is what I get you were trying to explain here, which is why, a neuron might need a 55 millivolt trigger, but that might require 4 different neurons at, what would that be? 55. We'll say it was 50. 4 neurons at 12.5 millivolts, each to trigger it. So maybe the picture here would be different, because I'm assuming that when you're explaining this, you're going on to say, well, we can do the exact same thing in neurUL so that we don't have false triggers, that, something only is triggered when the 3 inputs occur, whereas normal programming, it would have to be different. So maybe this just needs a different picture, and just explain it simply in that way, right? A secondary follow-on neuron has a specific action potential that needs to be reached, and that can be triggered by a single neuron, or in many cases, it will actually need, 2, 3, 4, 5 neurons. That blah 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 blah, and that's basically the same concept. I think that's all that needs. I think getting into like glutamate and GABA and all that type of stuff might be
too much.
I don't think it adds anything beneficial. It's more the abstract how it works rather than what the specifics are. So maybe change that picture. And then what was the next one?
Right. So the next one is this comparison.
Because then that goes into this. So this, I think, was okay. So correct me if I'm wrong. And I'm just kind of like talking out loud because it helps me understand it as well.
Yeah, sure.
So Lisp is, how would I term it? So Lisp is, or general programming is far more of a specific defined programming method, right? Whereas neurUL is much more of a programming method through abstraction.
Yes,
essentially, right?
It's more structure based. It's about the structure.
Correct. So you have to get this right structure, whereas in Lisp and normal programming, you actually have to get the right. I don't know what the word is. Yeah, the right native, right? You actually need the end result. You actually need to know what the result is going to be. Whereas in neurUL, you just have to say how that result is made up or what it is.
Yes, and which makes it more flexible and not rigid. Yeah.
So maybe this needs that more of an explanation and value, because here you're basically trying to convince people why neurUL is a better way to program than traditional programming.
So an explanation of why. This may not. Yeah. Okay.
So I think this is more important than the neuron stuff, because the neuron stuff is just like, well, this is how our brain works. This is how neurons work. But this is really, because you're going, as you've already you've had people talk about and say to you, well, like, I don't see what the benefit is, right?
Yeah.
So maybe this needs to be a bit more of it, and maybe even an example.
Right.
So so you've got the example of how neurUL would have robot poodle, but how would that concept be programmed in a typical programming language that we have now? Right. So we would, and I'm not a programmer like you, but we would, we'd obviously have to find a class called animal, and then that animal would have to be, does it blah, 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 so on and so forth.
Right. There's actually another language that we can add to this list, a more modern one, because Lisp is a bit old. So C#. And I think that's, I'm not sure about the popularity of C# compared to Lisp, but we can add it here as well, so that if there are others who would like to be, to see how it maps to current.
Well, I think, just an abstract concept, of how we would program something now using, I don't know if this is the right way to say it, but using, object-oriented programming, because we have to create an object and all that type of stuff, which is what essentially neurUL is doing.
I think it'll be a bit huge if we're going to go into that.
But no, I just mean like in comparison, because this by itself doesn't explain why it's better than the other way.
Okay.
If that, well, it does, but if you had a specific example and maybe spread this out over 2 slides,
I see. Okay.
Then you would be able to say, well, this is the way we do it now, but it's inflexible, right? Because we're assuming that we're going to have this, but with neurUL, because it's through neurons
to be able to do this.
It's at a much more, it's not it's not specific, but it's more through a descriptive way of programming. It's much more flexible.
Yeah. Okay.
Maybe just explain it that way, because this is way more important than all the neuron stuff.
Okay. All right. I think what we can do then is this slide. The first part will be this one, and then subsequent slide will be the further comparison of maybe an object-oriented approach of how we represent objects in C#, and then compare it with neurUL.
Yeah, so I think that would be good.
So we'll be able to show the benefits,
Yeah, to really show that it's different, why it's different. Well, obviously it's different, but why it's better and why it's more flexible.
Yeah.
Even just at an object, like a simple concept, like programming a robot poodle concept.
Yeah.
What was the next one?
The next one is the mystery game.
Oh yeah, that's fine. But otherwise it was fine. I just think, I think you've gone through enough with the neuron stuff in 101.
Yeah. Actually, we're about to transfer a couple of slides from the previous
I think even into this one or the other way.
Oh, we can put it there, back there.
Yeah, so I think even go back. So where you've got the other neurons. I mean, if you want, send me this link to this. Keep going back.
This one? Are you referring to this one?
Yeah, no, I think this is fine. However, I'm wondering if this should go after that other stuff, because basically you're talking about neurons, and then, okay, you talk about multi-neurons, you know, being triggering a follow-on neuron, right? Which then you obviously went back to the other stuff. But I think there's that missing slide in between that explains, you know, well, it's hard. But I'm saying, like, you're talking, like, the only thing I'm thinking is you're talking about this, and obviously the strength of neurons being triggered, which you go back to the other picture. Maybe even this should just be in 101.
These two.
Yeah, because in 101 you talk about, you know, the picture that you went back to when we talk about recognizing, you know, the sexy picture of Jennifer Aniston and then getting triggered. And this really explains how that neuron gets triggered, because there's multiple neurons that are firing, which triggers that follow-on neuron to have something. Whereas this seems kind of like out of it, if that makes sense.
Right.
Like, because I think this one you should be rather going straight way more into the neurUL as a language and programming and all this type of stuff.
And comparing it with other languages and stuff. Yeah.
Because otherwise you still, like, I think you're focusing a lot on the neuron, like on biological neurons, instead of getting into the meat and grind of this. But maybe even just like, instead of, because it depends on how far apart people are going to be viewing these lectures too. Are they going to be a week apart, 2 weeks apart?
Yeah. Actually, after we've done the finalized recordings, it would be really up to them if they watch it immediately.
But maybe even just like a recap of 2 slides.
Yeah, definitely. So we'll just go over the neural concepts very quickly.
And just the important ones.
And the important ones, and then proceed.
Like, you know, neurons are triggered because of blah, blah, blah. Multi-neurons are triggered because of this.
Yeah.
The fact that multi-neurons can, you know, a neuron might need a number of neurons to trigger it, allows our brain to have abstraction of concepts and not fire a neuron.
Unnecessarily.
Well, that can happen, but that's when we have disease, where neurons are fired when they're not supposed to, right?
Exactly.
But, you know, taking the same concept, that's you know, where neurUL basically comes into play and you know, starts, but, you know, you'll go into more explaining about that. But I think maybe that would be better. Yeah. Instead of trying to carry on I know you love the biology stuff, but you're going to be, you know, you're talking to programmers who are not, you know, scientists and biologists.
It might further complicate the topic. Yeah.
But if you just do a quick review and then get into this, because this is the part that's way more exciting, going to be more exciting for them.
Definitely. I think, but is the following slide fine then, that we're going to follow it with, can't go there, this. So we'll neuralize the samples in lecture 1A. That's all right? Because we're just building on the programming approach.
Well, that's where you've explained why, and then now you can, so that's going to be in this lecture, in this 102.
Yeah. Yes.
Yeah.
Definitely.
So this is where, this would be better, because then you won't spend 20 minutes explaining neurons again. Whereas leave that to 101. Because that's like the foundation. Like, you need to understand this, because this is how neurUL works.
Yeah.
But you just need you need an understanding of how neurons work, just so you can relate it to why this works, not because you need to remember how a neuron works.
Right.
Whereas this, you need to get back. you need to get into the programming, because the other thing is, I mean, you get people excited, but otherwise people might drop off because it's just, I don't know.
Too many details, yeah. Too many details. Yeah, I would agree with that.
Does that make sense? And
yeah,
I think for me, I'd rather you spend half an hour going through these examples than 20 minutes on neurons. Again, maybe just like 5 or 10 minutes, like recap.
But, the only question though is, do you think that is the case because you have a background in neuroscience, or is it?
Well, I don't have a background, but I did biology. But
biology.
It's more that I think that people don't need to understand that detail. I think like just simple. You know, we have just trust me. Like I've done this research. Like we have neurons that require multi-neurons to fire.
And it's up to them. It's up to them if they want to delve into that deeper, because it's just really okay.
And I mean, you could always have like if you're going to use a learning management tool to have these videos on neurUL, you could always have like just the text section or whatever, or if it's just a post, just the text section to additional resources if you wanted to.
So they can branch out, if they want to. Yeah.
But I just think because this is like your meat and potatoes, right, of what you want to start explaining. Especially because you're going to go into setting up the interface on your computer in the next one.
Yeah.
So this is kind of like your theory about creating your
neural network.
And your abstractions and all that type of stuff. So I reckon spend, half an hour, 40 minutes on this, especially if you're going to do it live, you're going to have people asking questions, right?
Yeah, definitely. I think I did 40 minutes.
Yeah, that was really short, this one.
This one was really short, and I think 10 minutes on the neurons. So, we can really transfer that.
I think it needs to be
transferred there.
Yeah, and not such an in-depth explanation.
Sure.
I don't think it's I don't think it benefits neurUL. Like it benefits you because you've, that's how it's built, but you just want people using it and seeing as a good way. Because you still need to understand how to program it right. But otherwise it's good. Like
the sequence is clear, right? We're able to build it up to really explain. Okay, until we reach the hands-on session.
It's a complex process. Like getting people invested in the first, 2 lectures is going to be important, right?
Yeah.
So you want to start having the neurUL stuff as quickly as possible, because people are going to want to go, well, I want to know how this works. But you're going to tell them, don't watch lecture 2 before you watch lecture 1. Like you need to understand.
Actually, I was talking to Carlos earlier this week, and I was thinking, do you think maybe we can start the hands-on process on neurUL 101? When we were looking at Jennifer Aniston, Zach Galifianakis, and then maybe too much.
Who's your target audience, though?
For 101,
I mean, just in general, do you want people who are already programmers? Do you want people who are just starting out? Do you want people who are just interested, or everyone?
Right. So maybe since 101 is like a very basic backgrounder, then we should just leave it.
It's only an hour. I think it's going to just complicate stuff more, because you're going to get into this in 102 and the theory, and then in 103 it's setting it up anyway. So it's only really 2 hours you need to watch.
So that's not too bad. That's not too bad.
No, I don't think so.
Okay.
Especially because the interface is still a little bit complex. Maybe when you have, in a year or two, when it's a really streamlined, simple interface to use.
Yeah.
Maybe. But just get people on board with it and excited about why it will work. That's my opinion. Other people might disagree or have a different idea.
That's all right. At least we have it here, and then we can discuss further. But anyway, I think I agree with that. I think we'll transfer 101. We'll see if there are any objections from the other contributors. But in any case, I think that's reasonable. Okay. All right. So is there anything else, guys?
I think I'm okay, Elmer.
Okay.
Thanks for the presentation. But I may have to agree on some point with Michael that it's just for me that you don't have to get into any deeper as to the neuron. I have a basic idea of it already when I watched the video, the first video that you sent me, the link. And going back into that very, and if you go into that very deep, then it might just complicate everything. But it all depends on the your audience and who you want to target. But for me, it's quite clear. But getting into that any deeper would probably,
okay.
Keep more complex.
So maybe,
but,
yeah.
Yeah.
Sorry, go on.
But generally, I was able to get a grasp of what's going on by watching the previous two videos and joining this discussion. Yeah.
Okay, that's great. Thank you for that. And I think, that's your observations are correct. I mean, if they want more details, they want to ask more questions, and it's up to them during the sessions anyway, right? So just stick with the basics, at least, not overwhelm them too much with the details, right? Yeah. Okay. Unfortunately, my father Nelson, he doesn't have a microphone, so I think, yeah, he doesn't have his microphone is not working. That's our home, by the way, in the video. You can see there. That's where I grew up. All right. So I guess that's it. Thank you very much for your time, guys. It has been a very a fulfilling 1 hour there. I think this is the second session, and we're getting somewhere now. And it's with your help, Michael and Dennis has been with us since last year. And my dad actually has been discussing neurUL with me for all this time now. And he's been very patient with my discussions because it's a really complicated subject. And yeah, thank you very much for your time, guys. Enjoy the rest of your weekend. And yeah, see you in the next session.
Cool. Thanks, Elmer.
Right, thank you.
Only logics can find.